Hi again. So now I want to build on the previous lecture where I went through some theory about the properties of conductors, and I want to build our first electronic device from some conducting materials. The device is known as a capacitor. Maybe you've heard of it before. So what's a capacitor? Well, fundamentally, it is two conductors that are placed close to each other, and what we will do with them is through some mechanism or other, we will transfer charge from one of the conducting materials, one of the pieces of conductor, to the other one. And so the most common and most useful configuration is to have our two conductors each be small plates, which are typically square or rectangular or circular, depending on such things, depending on what you specifically need. And so, for example, so here's one plate and another plate, and although there's no requirement that these be identical, they typically are. That's meant to be two circular plates. And then what we do is arrange some sort of physical connection between them. Typically, we attach a wire. This doesn't work. Typically, we attach a wire to one of the plates, and then we insert a source of electric potential, usually but not always a battery. And I will label this battery as providing an electric potential that I will call V. And so it might be 3 volts or 12 volts or 120 volts or whatever the potential difference happens to be. The effect of this potential difference, remember, as I said in the previous recording, that the potential is constant everywhere on a conductor. Well, this is a metal plate, so it's a conductor. Here's another separate metal plate, also a conductor. And it's hard to tell from this drawing, but I will make another drawing in a moment to make it clear, but let me say it out loud now. These two plates are not physically touching, despite what my diagram looks like. This is a perspective drawing. These are parallel to each other. They're physically not touching each other, and indeed there's usually some sort of an insulating material between the two plates, plastic or wax or something similar. So there's definitely no electric connection here. The only electric connection between the top plate and the bottom plate is through this battery with these wires. And what happens is, as a consequence of doing all of this, sorry, I had to go get some pens. The top here is high potential. The long line, maybe you've seen this before, maybe we've talked about it, I don't know. But anyway, this thing here, this is a symbol for a battery, like a C cell or a D cell or a AA battery or something similar. The top line, which is long here, the long line represents the high potential, and the bottom line is the low potential, and almost always we define the bottom of our battery to be at 0 volts. Remember, we're free to define our potential, we're free to define where our 0 of electric potential is located to be anywhere we want it to be. And so we almost always define the bottom of the battery to be our 0 of electric potential, and so then the top of the battery is whatever it is. And then your standard, like I said, C cell or D cells, AA's, AAA's, and so on, typically the potential difference is 1.5 volts, stamped on the side of the battery. So anyway, so this region here is at a high potential, down here is at the low potential, and so the model that we are going to use and choose is, even though we know better, we're going to imagine, we're going to pretend that it is positive charges that move from the top plate down to the bottom plate. I will discuss the reason for making that choice of imagining that positive charges move instead of the physical reality that negative charges move. I'll discuss the why of that another time, or perhaps we'll talk about it in class. But in any case, in this picture here, we're going to imagine or pretend or assume that the positive charges move. And in that case, with that assumption, well, the top plate here, again, it's a conductor, so every point on that plate is at the same potential, and they are electrically connected to the top of the battery, and therefore, the entire top of the plate is at the same potential as the top of the battery. Let's assume, just for the sake of being able to talk, let's assume that the battery is 1.5 volts, so it's a single AA battery or something. In which case, the positive charges are at a high potential here, or at least a higher potential, lower potential down here, and so they will spontaneously fall, that is to say, spontaneously flow from the region of high potential down to the region of low potential. The similar argument, the bottom plate is an equipotential surface. Every point on this bottom plate is at the same potential, and every point in this plate is therefore at the potential at the bottom of the battery, which we define to be 0 volts. So if I want to be even more accurate, I'd say the top of the battery is at 1.5 volts, the bottom of the battery is at 0 volts. So that makes the bottom plate at 0 volts and the top plate to be at 1.5 volts. And so that's the potential difference between the two plates. The result of all of that is that positive charges end up moving. Okay. And they make my drawing a little easier. The positive charges flow like this through the battery to the bottom plate, and the result is that the bottom plate ends up being positively charged because it got a whole bunch of positive charge. Meanwhile, the top plate ended up, since it lost a bunch of positive charges, it ends up with I'm sorry, I didn't say, but we assumed that both plates were electrically neutral when everything started. So the top plate then ends up with a net overall negative charge, and that's what happens. Okay. Now there's a lot of details that I've left out because I want to take this in small bite-sized pieces, but I will say this much. As the charge transfers, remember that we assumed that the two plates, the two conducting surfaces, were initially electrically neutral. So both plates had positive charge, both plates had negative charge, but they had equal amounts of each. As this transfer of charge that I just described goes on, though, both plates end up becoming increasingly charged. Two things happen as a consequence of all of this. One, the magnitude of the charge on each plate is always the same. At every moment in the charging process, the magnitude of the charge on the bottom plate and the magnitude of the charge on the top plate are inevitably going to be equal, inevitably because for every positive charge that the bottom plate gains, that comes from a corresponding loss of that positive charge from the top plate, because after all, these charges that we're dumping on the bottom plate came from the top plate. So every gain of a plus charge on the bottom plate is equivalent to a loss of that same positive charge from the top plate. A second consequence of that is that at every moment, as the charging process continues, the potential difference between these two plates is getting larger and larger and larger the more charge gets transferred. Eventually, and I'm doing a real executive summary here, that's why this is going so quickly, and then we're going to step back and take this more slowly. As the charging process proceeds and more time passes, more and more charge gets transferred. The result is there's a bigger and bigger electric field building up across this distance here, which means a corresponding greater and greater potential difference between the two plates. This charging process will slow down and eventually come to a stop. And it will come to a stop when the potential difference between the plates ends up being equal to the potential difference that the battery is supplying. Because what will happen is the electric field that is driving this process will end up pointing in the opposite direction. The electric field that the battery supplies ends up pointing in the opposite direction of the electric field that's building up between the two plates. So when the fields are equal and opposite, there's no net force driving charge anymore. The process, the flow of charge, the charging process slows down, eventually comes to a stop. And when it finally comes to a stop, we say that the conductors, that is to say this capacitor, and that's what the combination of these two conductors is called. We say the capacitor is now fully charged. And once it's fully charged, the flow of charge from the top plate to the bottom plate stops, and then the capacitor will just sit there with its charge sitting on the plates and then waiting for us to do something with them. Now, in the next recording, I'm going to go into this process in more detail, including some equations, and in subsequent lectures, we'll talk about why in the world you would want to do all this weird stuff. Okay, so next lecture.